Hi, my name is Mike. I'm a research scientist at TU Dresden and Fraunhofer AS. And today I'd like to talk about the big topic, how to place knowledge graphs in the GraphML research and in the GraphML community. And what are the tasks which will be trending next years. So in this talk, we'll briefly cover two big things: the basics of the knowledge graphs and how we use knowledge graphs in GraphML. So let's start with the definition. What are the knowledge graphs? And well, so far there is no one unified definition for that. One can say that KG is a set of triples, SPO triples, given entities and relations. Some person can say that, well, KG is something which has entities and relations, defines a schema, and covers several topical domains, and so on and so forth. Well, generally we can say that the common ground is that KG is a graph-structured world model. And those are, there can be many those world models. For instance, this is the, you see on the slide, the picture from linked open data cloud, and you can consider each of those small circles as its own world with its own schema and maybe some instances. And as you can see, there are many of them. Each of them is its own domain of discourse, and some of them are defined very rigidly, some of them are defined quite loosely. Still, those are small graphs which are unified into a big linked open data cloud. You can also think of it as a one giant unified knowledge graph or of interlinked other smaller graphs. So representing knowledge graphs, there are two big approaches. Well, as in artificial intelligence itself, there are symbolic approaches and there are vector representation approaches. And the symbolic approach, we use symbols. For instance, we encode triples as SPO, or in some functional form or in tuple form, and in vector representation form we map our entities and relations to some high dimensional or low dimensional space, and we build associated d-dimensional vectors to each of them. And well, symbolic representation is often used in tasks and some description logic or some logical task, reasoning tasks, and databases and data integration is pretty much everywhere. Whereas vector representation used in computer vision NLP and in our GraphML. And there are several like orthogonal tasks and features, something like open world assumption or closed world assumption, or some temporal graphs, evolving over time graphs, and how to deal with them as well. And depending on the chosen representation, of course, the approach will be different for them. So let's start with the basic symbolic representation, and we use triples. We use the formalism, which is called Resource Description Framework, or RDF triples. And here our example is Robert Downey Jr. You see that there are several movies, several studios, and several cities related there. Generally, we describe knowledge as triples, like RDJ resides SF, or RDJ born New York, and so forth. Then, for instance, like Iron Man, who was filmed on Studio Marvel. So this is how we use triples to encode graphs symbolically. So we have subjects, entities, we have relations, edges or edge types, and here are how they are organized. There is a higher level of complexity, I would say. The next level of representation, which is a rigid logical background, comes from description logics and some standards like RDFS or OWL. Those build semantics. They provide semantics for our knowledge graphs, and there are several levels. The big one, the most abstract one, is called T-box, or theory, ontology, schema. One can say that. And it defines axioms about classes. For instance, successful artist is somebody who acted in at least one blockbuster movie. Then we have assertion box, or facts, particular instantiations. Something like we asserted Robert Downey Jr. is a successful artist. That's how we do it. And there is also R-box, which says something about relations and how they are organized inherently. And we can say that acted in is subproperty of participated, because you can participate in much more things, whereas acted-in is more about like actor in the movie, but you can participate also in some event or Olympic Games, for instance. Alright, so on the other hand, there is embedding space, and the vector representation implies that for each of your entity and relation, you build a d-dimensional vector, and you will have in the end 2 big matrices of size number of entities by d and number of relations by d, and some chosen embedding approach. There are many of them. We'll cover some of them in the second part of the talk. And well, those embedding approaches essentially do some inherent clusterization of our entities. So for instance, in this 2D example, we have somehow built those embeddings, and well, we see that movies, for instance, are clustered together, cities are clustered together. And well, the point of those embedding approaches is to try to retain the semantics encoded in the graph. And well, depending on the algorithm, there is so much level of semantics which comes there. Well, we do not build KGs from scratch. I mean, we do not write them in a text file because there are many billions of triples there. Mostly we use either data integration or some information retrieval. So when we have structured sources like databases or some CSV files or JSON files, some loosely structured, somehow structured files, then we resort to data integration approaches. Whereas when we have some unstructured documents, corpuses of text, some other corpora, then we use information retrieval and natural language processing techniques. A couple of words on them a bit later. So how do we actually store and query those graphs? For that we use graph databases, and there are 2 competing approaches for it. The first one is well, RDF graph databases, and the second one is label property graph databases. They both allow to store and query graphs, but there are some important differences. Essentially, in label property graphs, you can have key value attributes over edges, whereas in RDF, you have only limited amount of them, so you cannot assign arbitrary key value attributes, but you can only assign those allowed by RDFS or OWL. And you query RDF databases with Sparkle, but LPGs you can query with Cypher or other languages. Although there are right now database engines that can translate on the fly those languages. Still, RDF allows for some logical reasoning because it has semantic schema. It might have an ontology in the background, but LPGs cannot do reasoning. They do not have semantic schema. And well, it's a small example of a query that given this triple that John knows Bob, we would like to know, to retrieve John and Bob based on the relation knows. So in Sparkle, it will be this basic graph pattern that we look for S and a friend. So S is the person, and he knows somebody who turns out to be Bob. And then Cypher, the format is a bit different, but the result is pretty much the same. But when it comes to key value attributes or complex limitations on the relations, in Cypher it's pretty easy. You can just tuck in this key value attribute, this set of key value attributes, but there is no easy way to do it in RDF and Sparkle. So that's why the community recently came up with 2 new approaches, soon to be standards, we hope, that RDF star and Sparkle star, essentially adding some syntactic sugar and some semantics and logics on the background. But generally what it says that we can describe the triples themselves. Adding those angle brackets, we can say, okay, that additional restriction that John knows Bob since 2001 can be attached to a triple in general. So, and this is how Sparkle star can essentially be integrated with LPGs as well. So on the bigger picture, what RDF star will allow us to do is to create more expressive knowledge graphs going away from triples. So here we can, for instance, assign more argument, more attributes that for what was internally nominated, and we can see, well, that RDJ was nominated for the Academy Award for work Tropic Thunder in 2008. So it's not that easy to just separate them and add as separate triples, because they need some context. RDJ can have different nominations, and you have to specialize what nomination it is. So using RDF star, it works. It's as easy as that. So you can just say, define a triple and add those additional attributes. And then Wikidata, if you know Wikidata knowledge graph, qualifiers are pretty much the same thing. So qualifiers also provide those key value attributes to the statements. So this whole thing with a triple and its descriptions will be called a statement. So in the end, what RDF star and LPG will do, we'll think that it will essentially converge to some unified model, and the peculiarities will be hidden by implementations, by engines who will be able to translate all those standards on the fly. And still, graph databases are better than relational databases, because we are in the GraphML section, right? And we still find we still find graphs more useful and more applicable in day-to-day tasks. Okay, so let's move more towards computer vision. Here we have a small example how we use graphs in CD, and then we'll look for NLP and GraphML. So a small example, small picture here, that we have an image, and then your favorite algorithm creates bounding boxes, identifies objects, and then we create a graph of relations between those objects. Or we create a graph of objects and how they interact with other objects. And having this small graph, one could also link those to a bigger knowledge graph and say that, well, this is not just a mountain. If you have a picture like with a bigger, famous mountain, you can actually link it to an entry from Wikipedia or from Wikidata to that particular mountain. Or it's not just a horse, but it's a particular kind of a horse, a certain breed of them, and so forth. So moving to NLP, how we can also attach KGs to, for instance, information abstraction. And this is a small example of on an Albert Einstein from Wikipedia. And we can build a small graph from this passage that Albert Einstein was born in German Empire, and he was a theoretical physicist and so forth. And those entities can be just entities, some spans from the text, or they can also be linked to a background KG, when you have specific entities for Albert Einstein or for German Empire and so forth. Of course, you can plug in your own KG and then shape the information retrieval system, so it will extract only those triples about entities and the relations you have in your KG. That's actually what you will do when performing those basic NLP tasks like named entity recognition. So for instance, you will say that you will need to disambiguate that this Apple, who is the CEO of Apple, Apple actually stands for the corporation, for the company, but here Apple belongs to which genus, here Apple is a fruit. And KG will provide you with a list of known entities and their description and so forth, and from the context and from the graph nature, it's very easy to map those words to a particular entity. So this apple to a company, this apple to a fruit, and similarly to an example here with the Iron Man to a movie character, and this Iron Man to a comic character. Similarly, with the relation linking, in KGs, usually you have lots of different, hundreds of relations, and you have their surface forms and some constraints, hierarchies. And it's easy, well, relatively easy, and there are multiple approaches how to utilize them for relation linking as well. So in all those questions, the highlighted word, it's the same synonyms we can say of the cast member, or they mean pretty much the same. And we would like to map those words to the cast member from the KG, known as the actor in the subject production, not to performer. Although performers semantically similar to the cast member, still cast member is a more correct mapping here. And then you can unify those in a basic question answering system against your graph. When you have a question and you would like to parse the question to a Sparkle query, and you have to build it based on the entities you found and relations you found. One interesting thing that NLP community takes from KG is especially in the language modeling, when your favorite whole, enormously large transformer architecture can also benefit from KGs, and especially in the masking task and the masking the language model. In addition to unstructured sources, you can use knowledge graphs with particular facts, with precise facts. And here Robert Downey Jr. portrayed Tony Stark. It can be inferred from the graph in addition to unstructured sources. And the fusion of the graphs and unstructured sources is one of the 2020 topics, or even 2021 topics, and KGs and NLP. So then let's move to the GraphML. And here knowledge graphs are, of course, one of different kinds of graphs existing in the community. In addition to knowledge graphs, there are scene graphs. We already seen them. There are some biomedical graphs. There are event graphs, or molecules, or some pathways and so forth. And they have their own specific parameters, and something makes them unique. And there are also some parameters that which make KGs unique, and those we'll be talking about next. So usually in the traditional setup, you have a graph, you have a certain encoder, graph encoder, which produces embeddings, and then you use them for a downstream task. Well, for KGs, the link prediction is used most often. First approaches for KG embeddings, they were trained especially only on the link prediction. It's not that common to train some systems on node classification. And almost nobody is doing graph classification, because KGs are usually, let's say, one big graph. You do not have molecules, or you do not have smaller parts of it. You rather have one big, huge thing. So it's pretty unusual in that sense to do graph classification, but we'll see what can be a particular use case of it. So, for instance, starting from the link prediction, there is a whole big line of research starting from 2011 or even earlier, who tried to measure the probability of a certain triple, and from that, inferring those probabilities, we build embeddings, and those help us to infer new links as well. There are several families of them, like tensor factorization or convolutional models. We'll not talk about them in details, but we'll just say that, well, there are different scoring functions, which depending on that scoring function, there is different expressivity of the models, and most of them are trained in a transductive setup, so they can only predict known relations among seen entities, and that's like a big difference, because a lot of traditional GraphML tasks, they are also working in an inductive setup. And another distinctive thing is that we do not have node features, so most of the approaches based on random initialization. Well, this is a small example how one of the recent models, Rotate, works. So it's a rotation and complex plane. And those are, you can dig it further, particular families or implementation of the models, what semantics they can retain. So training of them can be done in several ways. For point-wise thing, for instance, you have RDJ born in New York, and you just measure or try to maximize the probability of a correct triple. And negative sampling, it's something which is also very prominent now, like contrastive methods, contrastive learning thing. Well, it's been in the KGs and KG embeddings all the time. For negative sampling, we would like to teach the model to score correct triple higher than incorrect triple. So for instance, RDJ born in Ironman, that's definitely false fact. We would like to have lower probability score. And in one-to-one scoring, you score the pair of subject and relation against all existing objects. So like the transposed matrix of entities. And your negative samples are essentially all the other entities in the graph. So Well, here is a small shameless self-promotion that we recently released the library based on PyTorch for training KG embeddings. It's called PyKEEN. Recently, we have a stable 1.0 version. We provide you with lots of data sets, not just 2 or 4 standard data sets, but even more, some biomedical as well. A lot of KG embedding approaches. You can train them, of course, on your own graphs of various sizes and lots of different parameters, losses, optimizers, metrics, and so forth. We benchmarked all of them in a recently released paper. So we spent on that something like literally over 9,000 hours. So I would invite you to check it out, see how it works. We have also some integration with MLflow and weights and biases there. So let's move finally to the GNNs. The question will be, why can't we just plug in the traditional standard vanilla state-of-the-art encoders like GCN or GAT or GraphSage? Because they are so well studied. Well, there are several problems. We already know that, well, there are node features, and most of those approaches, they need node features in some way to work, especially in an inductive setup. We also have our knowledge graphs are multi-relational. They might have up to like 1,000 edge types. And most of those vanilla traditional approaches, they do not explicitly model edges at all, and they subsume that your graph is a homogeneous. It means that the link between 2 nodes is always of one type, whereas we can have hundreds or thousands. Those are big problems. And well, there are GNN encoders for multi-relational graphs. They have to consider entity and relation explicitly. And well, let's check out the evolution of them. So this is a vanilla GCN, and the aggregation over neighborhoods. You see just with one weight matrix and the hidden state of a neighbor. In our GCN, that's a relational GCN. To each relation, we have a square matrix or rectangular, any 2D tensor, WR. And then we consider already a neighborhood considering arcs. Well, it means that it leads to quite an over-parameterization, since we have a lot of rectangular matrices for, say, 100 or 1,000 relations, and for each of them you will have. There are some tricks to reduce this number, but still, this is quite over-parameterized. So further approaches, they already have explicit vector for a relation. So not just transformation matrices, but just a vector, and you have a certain composition function phi, which combines subject and relation. Here it's U and R, and then essentially you have only 3 different transformation matrices for input-output of self loops, and this reduces number of parameters, and it also works faster. And you see, well, that's still not a big difference from the original aggregation step from the GCN. Still, we have already here much more information tucked in. Here is a small example how HomeGCN works. HomeGCN is a recent work from ICLR 2020. And well, you see here, first we generate inverse edges and self loops. Of course, we need it for normalization. And depending on the direction of an edge, we first compose subject and relation. And then we multiply it with an incoming or outgoing weight matrix. And you can check out further details, of course, in the paper. So here is our big picture in like R5 and 5-dimensional space, how KGs can be placed in the GraphML. You have going bottom up and top down approach. So bottom up, you have a KG, you have a graph encoder, which gives you embeddings, and then what you can do with embeddings. Well, there are several big tasks like link prediction, node classification, entity matching, and curve embedding. Those two will check out in some details. And you also have 5 dimensions of KGs that define your setup, and all of them are pretty important. So you can work in transductive or inductive setup. Know that it's pretty hard for KGs to be inductive, and it's still an ongoing topic. You can have triple-based graphs, you can have hyperrelational graphs like those RDF star and Sparkle star we have seen earlier. You can have supervised and unsupervised setup. You can have a unimodal or a multimodal. Multimodal means that you have not only graph, but you also have text features, or you have some images, or you have sound and so forth. So it's a multimodal stuff. And of course, this the size is also a big thing to consider. And well, it can be pretty much a topic of your next paper. Just select something, flip a coin, and it can be like inductive node classification on triples with unsupervised setup, having unimodal setup on large graphs. How does it sound? So it sounds good for as your big next paper, right? All right, so let's see what happens, what exists in link prediction, inductive link prediction for triples and supervised setup. Well, this is pretty fresh setup. The work comes from ICML this year, and what's important that in the inductive part, you have unseen nodes, but no known relations. So in a training graph, there is a graph about LeBron and about LA and Lakers, but your test graph is about Stephen Curry. And there is totally disjoint set of entities, but still known relations. And you have to learn, well, at first you need some mechanism to extract features, node features, those node features we had problems with, and then train a model in that way that will allow for the inductive link prediction, that there is a link between, say, for instance, between Stephen Curry and California. Then we can go and see entity matching. So entity matching exists for transductive and inductive setups. Also, right now, currently in triple setup for supervised unimodal as well. And entity matching is about mapping entities from different graphs, or from different graphs. So in different knowledge graphs, for instance, you can have the same drug, but described differently. In DBpedia, there is ibuprofen with a set of relations and a set of values that it's known as ibuprofen, but in DrugBank, for instance, it's known as Femadon and with different ID. But based on their neighbors, we can still infer that it's pretty much the same chemical substance, and we can link them to the same real-world entity. So that's about entity matching and knowledge graphs. You can also do entity matching with graphs, say, based on images. So for instance, if you have the same points of a motorbike, then despite how you rotate the bike, you will still have something like a wheel or other parts, and they will still be in the same connection, well, logical connection. So generally you can see a similar pattern of the nodes on the graph, and then how you can match similar objects. So this is also interesting task for entity matching, and this is, you see here the architecture, pretty sophisticated architecture of that recent approach, deep graph matching consensus. It's also 2020 work. It's a two-step approach with source graph and target graph. You have a bunch of GNN encoders. You have some differentiable sinkhorn algorithm which is a neural version of a Hungarian algorithm for assignment problem. And I will encourage you to check out the work, the actual paper, to see what are the interesting tricks found. But still, those approaches can perform pretty well already, like reach 80%, 85% on entity matching data sets. And for matching KGs, they can work pretty well, matching about also 80 to 90% of multilingual knowledge graphs. So for instance, when you want to map not to different drugs, but say ibuprofen in English and some ibuprofen, some known in French with its French, with some French details. All right, and finally, let's check out what's happening in query embedding. So query embedding is a very interesting task. And by design, it has to work in transductive and inductive setups. And so far, it only works in the triples and the supervised setup. So you see, there is a lot of space to extend those models and to move the field a bit further there. Because right now they are quite limited. And so just transductive and inductive setup, okay, they do cover, but still all four other axes are still not that advanced. So query embedding is about answering SPARQL queries, but not against the database, but in the embedding space. So usually when you have a certain question where it can add incidences with Turing award graduate, for example, you have a query, SPARQL query, which you execute over some structured sources, like those databases. The problem is that those KGs are incomplete, they're pretty sparse, and they will only return you what is explicitly there. And it means that although the completeness will be full, but it's the completeness of only known things. You cannot infer new information from there. And the point of query embedding, well, we can embed the query itself into into the same embedding space as our entities and relations are, and perform reasoning right there. And well, this is a picture from a recent query to box work. It's also a picture from CS224W from the Stanford course. Some of you might have apparently seen it already. And you see the quality is pretty remarkable, that it's 99.9 for that for that not so simple query, which is pretty spectacular. So how it works, just one or two words, that it's a certain subset of SPARQL which works with conjunctive queries with some disjunction. So this query and this SPARQL query can also be reformulated as a conjunctive query, and based on that conjunctive query, we model several operators, like intersection operators, projection operators, and they are represented as boxes. And then you traverse those boxes, you collect those boxes, and you perform different operations with boxes and their contents to get the correct answer. So this is a very, very interesting field of like approximate query answering. And we expect it to grow much faster in 2021. Still, of course, maybe they're not that scalable as graph databases who can work with billions of edges very fast. Here it's still limited by size of your embedding matrices, but still it's something very, very promising. With that, I'm concluding my presentation. Those are the list of my social nets, so follow and drop me a line in Slack or somewhere else, or all on those social media. Subscribe to the GraphML Telegram channel. We'll be happy to see you there. And thanks for watching.